Out in the far reaches of the North Pacific, there's a sea that moves to its own ancient rhythm. It's a place of vast gray horizons and a deep, quiet cold that feels like it comes from the water itself. This is the Okhotsk Sea, and for just a few months every year, it goes through a change that just doesn't make sense for its place on the map. It stops being a sea and becomes a river of ice. Let's explore the secrets of this incredible frozen river.
So, the story of this sea really begins with a puzzle, a kind of geographical riddle. If you were to actually trace the very edge of winter sea ice across the entire northern hemisphere, you'd find its most southern point is right here in the Sea of Okhotsk. It's a total outlier, a climatic anomaly that by all logic just shouldn't exist where it does.
And to really wrap your head around just how strange this is, think about its position on the globe for a second. This sea sits at about the same latitude as central France. Yeah, France. Or the United Kingdom. These are temperate places, right? You think of green landscapes and mild oceans. They are definitely not places you associate with these sprawling, Arctic-style ice fields that take over the Okhotsk every single winter. It's like a silent white continent forming and breaking apart in a place it just doesn't belong.
So what we have here is really a sea of contradictions, a body of water so far from the pole that acts like a polar sea. It's a place where these immense forces, the scale of the continent, the raw power of the atmosphere, and the slow, patient flow of a massive river, all conspire to create a world that feels both ancient and fleeting. A landscape built from water that's solid, but is always moving.
And that brings us right to the heart of the mystery. How on earth can this sea, so far away from the true Arctic, put on such a polar show? Well, the answer isn't just one thing. It's a convergence of powerful natural forces that are just perfectly aligned. It's a precise and delicate recipe for making ice, perfected over thousands of years.
To really understand this frozen river, we have to go to its source. We need to travel to the northwestern shores of the sea, a remote and windswept place where the land of Siberia meets the water. This is the nursery. This is where the ice is born.
Three absolutely critical ingredients come together in this one specific spot. First, you've got the relentlessly cold breath of the Siberian wind. Second, the enormous steady flow of one of Asia's great rivers, the Amur. And third, a uniquely enclosed geography, a basin that basically acts as a container, trapping and concentrating those first two ingredients.
So, ingredient number one is the air itself. The winter winds that hit the Okhotsk have traveled over the vast frozen interior of Siberia, a region so cold they call it the Northern Hemisphere's cold pole. This air arrives carrying temperatures of minus 40 degrees Celsius, sometimes even colder. It's an intensely dry, heavy, and frigid mass of air that acts like a natural flash freezer, just stripping the heat from the surface of the water with this brutal, silent efficiency.
Now for the second ingredient, which comes from the land. The Amur River, after traveling for thousands of kilometers, pours a massive volume of fresh water into the sea. And because fresh water is less dense than the salty ocean, it doesn't mix in evenly. Instead, it spreads out, forming this distinct, buoyant layer right on the surface, a lens of low salinity water about 50 meters deep. And as we all know, fresh water freezes much more easily than salt water.
There's a name for this phenomenon. It's called salt stratification. And honestly, this is the absolute key to the whole secret of the Okhotsk. See, in most of the world's oceans, as the surface water gets cold, it gets denser and it sinks. This brings warmer, saltier water up from the depths in this constant mixing cycle. This whole process makes it incredibly hard to freeze the ocean's surface. But here, that low-salt surface layer from the Amur is so much lighter, it basically just floats on the saltier water below, creating a stable, unmoving cap. Now, that brutal Siberian wind only needs to cool this shallow 50-meter layer to its freezing point, not the entire depth of the sea. It's a total game changer.
And the final ingredient is the basin itself, the stage for this whole drama. The Okhotsk Sea is almost entirely hemmed in by Russia's Kamchatka Peninsula, the Kuril Islands, and the huge Sakhalin Island to the west. This geography acts like a container. It holds the Amur's fresh water near the surface, stopping it from just dispersing into the Pacific. And it shields the sea from the influence of warmer Pacific currents that would otherwise mix in and disrupt this delicate freezing process. It is the perfect, isolated laboratory for making ice.
So once this ice is born in that frigid crucible in the northwest, it doesn't stay put. It begins a long, slow journey southward, transforming from these individual fragile crystals into a vast and powerful moving landscape. A migration begins.
The journey kicks off right in the mouth of the Amur River. In that super chilled surface water, tiny needle-like ice crystals start to form. They're called phrasal ice. These are the seeds of the great ice flows to come. At first, they just give the water a kind of soupy, greasy look, but as the temperatures keep dropping, these countless little crystals begin to coalesce, kneading themselves together to form thin, fragile, almost translucent sheets of ice on the sea's surface.
You know, there's this really evocative phrase that people who live by this sea use to describe the ice. Russian-born, Japanese-raised. And it's more than just poetry. It captures a deep truth. The ice starts its life in Russian waters, a product of the Siberian winter and the great Amur River. But its destiny, its maturity, and its eventual decay lies far to the south along the distant shores of Japan.
The very same powerful winds that helped form the ice now begin to push it away from the coast, and it gets caught up in the steady, southbound pull of the East Sakhalin Current. This combination of forces herds the newly formed ice sheets, compressing them, rafting them over one another, building up their thickness and their strength. Slowly, they merge into a vast, cohesive stream, a literal frozen river, hundreds of kilometers wide, flowing through the open sea.
After a journey that takes weeks, covering hundreds of kilometers, this frozen river reaches its final destination, the northern coast of Hokkaido, Japan, and its arrival is a dramatic, transformative event. The dark, open water disappears. It's replaced by a silent, white world of shifting ice floes that groan and press against the shore. It is a landscape that feels more like the high Arctic than temperate Japan, a world completely reshaped by a visitor from the far north. But the story of this ice isn't just about physics and geography. It's also a story of biology, of profound creation. What happens during the ice's formation and its long journey sets in motion a chain of events that makes the Okhotsk Sea one of the most productive marine ecosystems on the entire planet. This seemingly barren ice is in fact an engine of life.
So, you have to wonder, right? What is happening beneath this seemingly lifeless frozen surface? Well, the answer lies in a subtle process that begins the very moment the first ice crystal forms. A process that invisibly connects the surface of the sea to the deep, dark ocean below.
The process is called brine rejection. Here's how it works. As seawater freezes, the ice crystals that form are essentially pure water. They push out the salt molecules. So the pure water freezes, but the salt gets left behind, concentrated in the unfrozen water nearby. This creates pockets of liquid that are not only intensely cold, but also incredibly salty, and therefore incredibly dense. Way denser than any of the water around.
And because this brine-rich water is so dense, it sinks. And it doesn't just sink a little, it plummets downwards in these cold, salty plumes, creating a powerful vertical current. This is a form of deep water formation, a process known as ocean overturning. This water, formed in the shallows of the Okhotsk, sinks all the way to the intermediate depths of the ocean, between 200 and 800 meters down. It becomes a critical part of the engine that drives ocean currents across the entire North Pacific.
And that sinking water carries something vital with it, the micronutrient iron. The Amur River brings in iron-rich sediment from the vast interior of the continent. The constant formation and movement of ice stirs up even more iron from the shallow seafloor. And as that dense brine sinks, it acts like a biological elevator, carrying this essential, life-giving element down into the deep ocean currents, which then distribute it across the otherwise nutrient-poor expanses of the North Pacific.
The unique life that this system supports is as beautiful as it is strange. Perhaps its most famous emblem is the Cleone, the sea angel. This tiny, ethereal creature is a type of shell-less snail that just flits through the frigid, nutrient-rich waters on delicate wings. It's like a living jewel, a beautiful and fragile symbol of the hidden vitality that the harshness of the sea ice makes possible.
But this entire, intricate system, from the physics of ice formation to the delicate chemistry of nutrient delivery, is built on a seasonal rhythm, a cycle that has repeated for eons. And now it is facing a profound, long-term threat. The frozen river is changing.
As the relentless cold of winter finally recedes and the light of spring returns, the cycle reverses. The great thaw begins. The vast fields of sea ice, which have traveled hundreds of kilometers and locked away essential nutrients within their frozen matrix, begin to weaken, to fracture, and to melt back into the sea.
And as it melts, the ice delivers its final, crucial gift to the ocean. Research estimates that every spring, the melting ice releases up to 30,000 tons of life-sustaining iron into the surface waters of the southern Okhotsk Sea. 30,000 tons. It is a massive annual fertilization event on a scale that is just hard to comprehend.
This sudden enormous injection of iron, combined with the strengthening sun, triggers an explosive bloom of phytoplankton. These microscopic plants are the very foundation of the marine food web. This bloom is so enormous, so rich, that it sustains not just the Okhotsk Sea itself, but also the famously rich fisheries of the wider North Pacific. It connects this seasonal ice to the health of an entire ocean and ultimately to the food on our plates.
But this engine is beginning to falter. The data on this is clear and unambiguous. Over the last 3 decades, as the upwind region of Siberia has warmed at an accelerated rate, the total area of sea ice formed in the Okhotsk has decreased by about 20%. Less ice means less brine rejection. Less brine rejection means the ocean overturning that critical deep water pump is weakening. And a weaker pump means a risk of drastically reduced iron delivery to the deep ocean.
The scientists studying this system state the stakes in stark, unequivocal terms. They say, if global warming weakens sea ice production, iron supplies will decrease, reducing levels of biological productivity and fishery resources. The chain of consequences is direct and deeply worrying. The health of this entire oceanic ecosystem is tied directly to the annual formation and melting of ice.
And so we're left with a final, contemplative question. The Sea of Okhotsk is more than just a geographic anomaly. We've seen that it's a planetary engine, a biological pump for the Pacific, a nursery for its vast ecosystems. It is a frozen river, carrying with it the very possibility of life. As this river shrinks year by year, what becomes of the life it carries? The quiet, cold sea has shown us the delicate balance. The question is whether we understand it in time.